Okay. Hello everyone, my name is Kelton Kersley, and today we're going to be talking about electric field lines and equipotential lines. To start off, I want to give a brief introduction / demo because those are cool, right? So what I got is I got two different pieces of tape. One's a positively charged piece of tape and one's a negatively charged piece of tape. Pretty easy, you can do it at home. Just put two pieces of tape on the table and pull them apart, and then you got different charges of tape. But what I'm going to do is I'm going to put a negative charge on this rod, and we're going to see how this affects the two different pieces of tape. So as you can tell, our positive charge is attracted to our negatively charged rod, whereas our negatively charged piece of tape is repelled. So two opposite reactions or interactions with this rod. So that's got to tell us that there's two different forces or two different things that are happening. So this can be explained by our electric field lines. Here, electric field lines represent a force around a charge. So like we saw with the rod and the positively charged, they were attracted. So there was like a force in between those two that were attracting those two objects. Whereas with the negatively charged piece of tape and the negatively charged rod, we saw a repulsion. So an opposite force in the different directions. So what electric field lines do, they just represent the force. They're a picture of the force and the way that it's being pushed out or drawn in. So as we have here, I have these two different representations. I have a negatively charged particle and I have a positively charged particle here. Positively charged particles always point outwards. They always point away from the positively charged particle, whereas the negatively charged always points in. So a way that I always like to think about this, sort of a moral in life, is like positive people are always pointing outwards. They are always happy or trying to look to how for different ways on how to help people. And negative people, they're always sort of like focused on themselves. So that's one way that I like to think about it. In a different, just like a different way for you to remember what ways the forces are pointing out. Along with our electric field lines, they also show the magnitude of force. And so magnitude is related to how close the lines are and how many there are. So in this example, we only have a few lines in comparison to this one that has many more lines. So this shows that this particle has a much stronger charge. The electric field is much stronger here. The strength of an electric field also is proportional to the length or the area away from the charge. So in this case, the lines get closer together as we get closer to the charge. But as we point out, those lines start to spread out. And this means that the electric field becomes weaker. The further apart the lines are, the weaker the charge is. As well, so like these also explain Coulomb's law, if you've heard of that before. It's basically a law that explains how force is related to the charge of a particle in relation to the area that is surrounding it. And that's explained by that, where Q is the charge, K is a constant, R squared represents the force, or the area, sorry, and then F represents the force. So we're going to go on to a few more pictures. So here's a couple more diagrams. When we have like two of the same charge that come together, like we saw, we see a repulsion. So this is what is happening in between those two. These lines never cross. They're the same, they're always pointing out. And so they're never going to touch each other. That's why they are pushed away from each other or push each other away, because they point in the same direction. And that's with positive lines, and the same thing with negative lines. This is like a visual demonstration of like what we saw with the tape. where we have two negative charges. The charges are coming in, but because they're the same, they repel each other because they never cross. That's one thing you always want to know, is electric fields never cross. Let's see. Okay, we're going to go on to another example of what happens when we have two of the opposite charge. So in this example, we have a positive charge here and a negative charge. And so what happens here is we always start with the positive charge, and the charge always ends up in the negative charge. And so it's just a complete circle. Start with the positive, end with the negative. And they all bend to conform to each other. So that's pretty much about it for equipotential lines. It's not too complicated, pretty simple. If you have questions, you can comment below, as always. But now we're going to go on to equipotential lines. So equipotential lines, they're pretty related to electric field lines. Only equipotential lines are places where the charge are the same. So yeah, equipotential lines are a representation of where electric potentials, or aka the voltages, are the same on the electric field lines. And here's sort of the equation for this right here. So electric potential, or V, or voltage, is equal to our constant multiplied by our charge divided by our radius. And so as you can tell, our area also has an effect on this. However far away we get from our electric charge, the less powerful the electric field will be, and also the weaker our electric potential will be. So these are all described or drawn out like this. So as you can see, we have our electric field lines here pointing out, and our equipotential lines are surrounding our charge, and they all hit our electric field lines perpendicularly. So we'll go on to this spot. So here's a few key things to know about it, or to know about equipotential lines. On an equipotential line, it requires no work to go along that line or to move a charge along that pathway. And so this is an example of it. So this is work is equal to the negative change in potential energy, which is also equal to the charge, or the negative charge. Sorry, that's a negative sign. This is charge, and this is the change in voltage. But because we're in an equipotential line, and it's a one spot all the way around that charge where the voltage or the electric potential is the same, we don't have a change in voltage. So therefore, we just get a 0. So no work is required to move along that equipotential line, or move a charge along that. So since there's no work required to move a charge along an equipotential line, then equipotentials must be perpendicular to the electric field. And this is an equation to show that as well. So work, if you might have learned earlier, work is equal to force times distance times the cosine of the theta of the force. And that's also equal to the charge times the energy times the distance from the charge multiplied by the cosine of theta. And so we know that all of these all have a value. We know we're going to have a charge, we know we're going to have an energy because of that, and we also know that we're going to be some distance away from the charge. But that means that this cosine would have to equal, this should be 90. This cosine should equal 90, which would make that 0, and which would also mean that work is 0. So that's a little description. Again, if you have questions, comment below. And now I'm going to show you a couple of diagrams of what this looks like when we have multiple charges. So in this example, this is more than just the new start of a design of Spider-Man. this is actually two different charges. So we have a plus charge and a negative charge. As we have in the other one that we saw previously, we have our electric field lines, and then we have our equipotential lines, which are in black. And so as we get closer to the middle of these, you'll see that these equipotential lines are getting pretty close. They're all very close to each other. And as we get further away from getting in between these two, they start to spread out. So this shows that when we're like closer together, when we have our lines closer together, that means that there's a greater rate of change. And I'll give a couple more examples of that later in a couple other demonstrations. So that's that with the opposite charges, and with the same charges, it's sort of different. So we'll see that we got these two charges, and then they connect because they don't touch, but the equipotential lines will go around those. So yeah, just remember that the closer the lines are, they indicate a greater rate of change. That's pretty much one of the big things that you need to know about that. So like I said, we're going to go into like another demonstration. This is just like another example. So what we have is like nylon mesh fabric here, and we got two beads. And so as I pull down on this, this will represent two of the same charges because they're pointing in the same direction. And then as we point our laser here, you'll be able to see sort of the formation of it. And this really helps me understand, so hopefully it helps you guys. So if you can see it here, I sort of got like the same image or picture as what I had on the board. So we have like a circle around it, and then they connect right here. So that's sort of something that helps me understand it. Hopefully it helps you visualize it. But yeah, thanks for watching. Give me any questions you got. I'm here for you. Thanks. Hope you have a great day.